So it's my pleasure to introduce Tom Terwilliger, the final speaker of the day. So Tom is a founder member of the Diffraction Data Deposition Working Group. He was the agreed nominee of the Commission on Biological Macromolecules of the IUCR, and I believe is now its chairman. He's also the incoming president of the ACA, and I think you will agree with me with the vision for realizing the Living PDB and how raw diffraction data and its metadata can help. Tom has his finger on all the pulses.
Thanks, John. Yes, it's a delight to be here to talk to you about this. You know, this talk is on continuous improvement of data, of interpretation of data in the protein data bank. And actually, when I started off pushing this idea, there was a lot of resistance that this just didn't seem like a practical thing, and there's all these challenges to doing it. But a couple of weeks ago, I was at a workshop that the protein data bank organized. It was on a validation of ligand structures, in fact, and this issue came up, and it was obvious that of course we should do this. It was like, wow, this is really catching on. So maybe I'm just going to be preaching to the choir here for the next minutes, which would be the easier thing to do than usual. So this talk is basically coming from a paper that Gerard Bracogna and I published last year. There was a series of papers that were published based on the diffraction data deposition working group, and this was just one of those. And so let me give you a little background here. The idea of reanalysis of deposited data goes back a long ways, and here's one quotation from Gerard Klavek and Alan Jones' group. After they developed a server, the electron density server. There's basically a tool to allow anybody, and it's there today, it allows anybody to look at the electron density for any structure in the PDB for which structure factors have been deposited. So basically, looking at those maps allows you, the user, to evaluate with your own eyes, as we heard earlier today, whether or not a structure is likely to be right, or whether or not a particular feature of that structure is right. And you don't have to own any fancy tools in order to do this. You just go to the web, and you can look right there, or you can download the files and look at them on your own computer. So this is a very nice tool, and they came up with the idea that, yes, perhaps this whole structure database should be dynamic, not just a fixed, here's a structure, take it or leave it, but maybe we should be updating these as things go on. More recently, Robbie Justin, Bracogna and Gert Vried and others developed a pipeline that they call PDB Redo that was alluded to earlier today also, in which the structures in the PDB for which data are available, structural factors are available, are continuously re-refined and actually remodeled at a certain level as well. So you can go to the PDB Redo site and you can download a version of any structure that's in the PDB that is basically the best automated structure you could get using the tools that they're using that starts off with the structures in the PDB. And many of these are demonstrably less inaccurate than the structures that were originally in the PDB. So there's already significant merit to going to that site to get your structure rather than one from the PDB. I wouldn't necessarily take everyone from there yet, but certainly the direction is the right one. And they made some arguments why this is a good idea, and amongst them, the last one there, it's good for the depositors. So this is kind of one of the worries, like, well, I deposit my structure, that's my great, wonderful structure, how can anybody ruin it? But in fact, these guys are going to make your structure even better, and you still get credit for it, so what's wrong with that? And so lots of ideas to do that. So why are we even talking about this? It's obvious, right? I already told you people are feeling it's obvious. It's because the current paradigm is not what I just described. So the protein data bank is, and for the foreseeable future, will remain the definitive repository of macromolecular structures. It's really unique in the structural biology, in the biology world, that there's really only one place. This is the place where if you want to get a structure, it's going to be there. And the crystallographic community sees the PDB as its archive of models and data, and the biological community, which is much, much bigger, uses the PDB as its essentially only entry into structures. If they want a structure, that's where they're going to get them. And it's very important to recognize that other repositories like PDB Redo would have to add major value to these structures to be widely viewed. And they're not widely viewed, anything like the PDB is at the moment. So that's an important issue, is that the protein data bank is totally special. Now, how does it work in terms of structure determination and analysis? Well, right now it's really one-time thing. A crystallographer, their team, determines a structure. They deposit the data now that goes with that structure and their model, which is their interpretation of the data. And that's basically it. And it is possible to update these structures. It's easier for the depositor to update the structure than for anybody else. Basically, the original depositor can remove the original and replace it with another deposit, and then that becomes the definitive new structure. Anybody else can reanalyze and deposit another version of that structure, but doing so requires a publication to go with it, and B, it's a lot of work, and C, the new structure is, for all intents and purposes, not associated with the old structure. It gets a new PDB identifier. Of course, there will be a link that says that this is highly related to a previous one, but there's no link that says this is the exact same data except in text. So it's basically like a new structure. It's poorly linked. That's today's version. This will all be changing. The PDB also is on board that it's obvious this has to change. This is all very good. Now, another important aspect of this is the historical focus has been on the model, on the interpretation, not on the data itself. So you deposit a PDB structure, it's the structure, it's the coordinates that are the thing that everybody thinks about. It's the coordinates that originally got the identifier, and then later as an afterthought, with a lot of work, the structure factors started getting deposited along with that. Okay, great, but those are like an annotation of the model rather than the other way around, which you would imagine makes much more sense. And there's only rare reference to the data itself. It's really the reference to the structure, the coordinates. And the community, the biological community, doesn't see the data at all. So, why should this be different? Why doesn't this make sense, the current state? Well, to me, it doesn't make any sense at all. And one is the reinterpretation idea is totally feasible. So PDB redo has demonstrated that you can automatically reanalyze structures at a high level and with high throughput. So it's feasible to do that automatically, even though it's not perfect yet. But surely that'll get better. And as software improves, that capability will be extended. Third, validation procedures exist to evaluate model quality. I'll mention this later. And the protein data bank itself is spending a lot of effort on developing standards for validation of protein structures and of the data. And importantly for this meeting, the availability of raw images will extend the capability of reinterpretation even further. So an expert reanalyzing images can often obtain data that are far superior to the data that the process data that are obtained by routine application of even their own tools. And just an example of that, recently I was working on methods for solving structures by sulfur SAD, and we had some structures that were very challenging to solve. We obtained the data from the original depositors, and we tried to solve that, and we could solve some of them, but only with great difficulty by merging them together. And then we sent the same data, or the same data went to Spisak Achanowski, who was Vladik's companion, who works on the data processing, and Spisak reanalyzed all that data. And then suddenly, a lot of these structures could be solved that basically couldn't be solved before. So an expert, but not super expert, is not the same as a super expert, right? So, and these processes will always be getting better, right? So it is surely true that down the road, we will be able to take the exact same images and obtain much better, more accurate structure factors, and therefore more accurate phases, and we'll get better models. And this, might say it doesn't really matter, you only can change small things, but actually at lower resolution, a little bit of difference can make a huge impact. And so our structures may well be dramatically improved by doing this. Okay. And reinterpretation is a good thing to happen. It's not only feasible, but why would we do this? Well, you can fix minor errors. Many people, including some in the room, Vladek has published papers particularly on validation of metal ions, for example, in structures. Others here have also published structures about errors in structures. Surely we can fix the little things. And maybe we'll fix the big things as well. So why leave these errors in there if we know how to fix them? Another thing is you might be able to get consistency amongst related structures by using consistent methods. So just imagine a situation where you're solving the structures of a whole bunch of proteins that are more or less the same with different ligands or something like that. And what you're really interested in is the differences between these. Well, if you use a different software package for each one, and you allow the side chains to refine to different conformations in each one, you get a whole bunch of differences that are totally superfluous, that are irrelevant. But if you did everything totally consistently and refined all those structures together and only allowed differences amongst them that are required by the data, surely you would get more accurate differences that way. So that kind of thing is the kind of thing you might imagine people doing in a systematic way if you are basically allowed to reinterpret all these structures. Of course, you can do that today, but you can't make it available to everybody in an easy way. You might have new formulations about how you even describe structures, multi-model descriptions of structures, yeah, the other ones I really talked about, joint refinement of structures. Okay, so why hasn't this happened already a long time ago? So it's really a cultural thing. And the interpretation of a structure is basically owned by the person who solved it. So I solved my structure, I spent a whole lot of effort at getting it there, I deposit it in the PDB, and then everybody in the world knows that's Tom's structure. And then if there's something wrong with it, it's my fault and everything, but basically somebody else just goes and takes my data and reinterprets that, there might be conflict between me and them. And we don't want that, right? And that's just a cultural thing, there's no reason why that should be that way. But why is it? It's because I spent a lot of effort making that structure, right? And if somebody else fixes it, I might look at that as criticism of me instead of an improvement in my model, right? So we need to fix that way of thinking in order for this whole thing to change. So I need to feel that when you fix my structure, you have just made all this better and you have put more value into my structure, and so I feel good too. That's how we have to have it, right? There's some practical issues too. So if there's multiple, suppose there was some way to have lots of interpretations of the same data. Well, you, the user, the biologist, well, which one should I look at? They're all kind of similar, but everyone is different, and I might get a different interpretation of the thing I'm actually interested in, depending on which one I look at. So how do I decide, right? So that's a big issue, not totally solved, and that's a really important one. And along with that, if I make a new structure, which one's better? How do you decide what's improved? A minor point is that the original depositor, they might have access to some specialized information that they didn't specify as metadata. And if so, maybe an automated repeat or my own repeat later might not do as well. So we need to keep that kind of thing in mind. Another reason this doesn't happen is because deposition is a big job. Okay, so if we're going to continuously improve structures, what might it look like? Well, it could be systematic optimization of all the structures. That's PDB redo, just continue that, make it better, great. Redetermination of groups of related structures, I talked about that kind of idea. Or redetermination of certain groups of structures where you're focusing on specific questions. Maybe you're going to look at just metal-containing proteins and look at all the bond lengths that are in those and really refine every structure in order to obtain that information most accurately. So that'd be a perfectly fine thing you might want to save and let other people have down the road. And so what do we have to do if we want to make this all happen? So we really need a way to validate the data and have available to us validated processed data and metadata so that a person can start now, starting off with the original structure perhaps, or maybe starting from scratch, and redo everything and have all the information that's necessary that was also available to the original depositor. So we talked here a lot about collecting metadata, and this is just totally critical, right? Because you have to have a way to transfer the information that the original person had to a person later so that they can do the optimal job in developing a new model. And I think it would really be ideal for the deposited data at deposition time, basically to one of the validation checks would be taking the deposited metadata, and eventually just redoing the structure determination with those and validating that the answer you get is pretty much the same thing as the depositor got. Right? So today it's not very feasible, it takes too much computer time, blah, 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 but that won't be a limiting factor down the road, right? So no particular reason why you couldn't do that. So that says, yes, at least using today's technology, we get pretty much the same thing they did. They must have deposited the right amount of metadata. If they didn't do that, then we wouldn't be able to get the answer, and you just send it back to them and say, give us enough data so we can reproduce what you did, right? Seems pretty obvious. All right. You also need unmerged data. So John Westbrook talked about this a little bit before. It's really essential to have unmerged data or the images themselves in order to do this validation process well. So we haven't really talked about it so much today, but basically the estimation of errors in the intensities of reflections is not as is difficult to do accurately. And particularly for, say, measuring anomalous differences and estimating the uncertainties in anomalous differences that go into phasing and so forth, it's very hard to get those numbers right. The most powerful way of getting that number pretty accurate is to have multiple measurements of the same things, and in order to validate whether or not somebody did that correctly, you need all those multiple measurements of the same things, or you need the raw images so you can redo it from the beginning. So these things are totally critical. So the raw diffraction images that we're talking about today are by far the best way to do this. Okay, so just a couple more slides here on what do we need to do to make this all happen. So if the original depositor's structure is not going to be the only structure that the protein data bank or somebody else serves up, you have to have a way to decide which one to look at. And so I make a point here about the views. The protein data bank is the protein data bank RCSB, and in Europe and Japan. There are 3 different portals, and they actually give slightly different views of the same information. The PDB, the www.pdb.org is by far the most hit, I think. And so whatever they put on their website, that's what a lot of people are going to see. So which structures they serve up, and same thing for the other versions of the PDB, have a huge influence on what people are going to think or what they're going to do. And the model that's appropriate for a particular use may depend on what that use is. So I was just giving you some examples before. If your use is what are the bond lengths for metal atoms to their ligands in proteins, then you want a certain way of having handled that data and a certain pruning of all the data in order to do that. On the other hand, if you're just interested in what's this overall shape of my molecule, then you don't care about those things nearly as much, right? And so eventually, it will be necessary to know what is in the user's mind, what am I going to do with that structure, and then serve them up a structure that is most appropriate for that use. And there will presumably always be some default thing, which might be just, for example, the highest resolution structure, analyzed most recently with the best statistics in some measure, right? So you might serve that up, and of course the PDB would always also serve up the very original one if people want the original interpretation, which is always going to be there, right? And so how are we going to go about doing this? So as I say, we need a way to serve up the right model, and you have to have metrics for making those decisions. And so this is what many people are working on right now, is the idea of you have a list of structures, a list of possible interpretations of the same data. How do you rank these different interpretations for different uses, or just for validation, which structure is most likely to be closest to the right answer, right? And there's no firm answer to any of these things. The PDB is working very hard on developing tools for this validation, though. And so in this slide, I'm illustrating some of the things that are happening along these lines. So number one, there's a lot of discussion now about the idea of versioning of structures in the PDB. Instead of having a new PDB deposit for a new interpretation of the same thing, there's just one data and one PDB identifier goes with the data, and then versions of that same thing. And those could be versions that would be the same depositor replacing it might be a version, or somebody outside making a new version that might be a new version, et cetera. So it's just a conceptual thing. Now everything is associated with data, and there are different interpretations of that data. So that makes more sense in terms of serving things up. And then validation, as I've been talking about, in the protein data bank now, the PDB has task forces for each overall class of data, like X-ray data, EM data, and so forth. And for each one of these, the task forces have the responsibility of identifying criteria, numerical measures that can be used as criteria to identify are there problems or not problems with this structure. So the protein or X-ray validation task force went through that exercise a number of years ago, came up with a long list of calculations to be made, things such as bond lengths, clashes, agreement with the density, et cetera, a long list of these things. And when you go to the PDB today, you can download, by clicking, a long sheet that lists the results of all those things. Now, one might say these reports need a little bit more work so that they're easier to interpret. That's just a minor technical aspect of it. The reports themselves are very, very valuable. And the PDB is continuing to upgrade and update these validation reports. And the basic idea is these validation reports will be available to users of the PDB. They'll be available, we hope, to reviewers always before accepting papers. And then down the road, the same information can be used for serving up the right structure for each purpose. So that's where I think we're going to be going here, is we'll have metrics that say what are the numerical criteria for how the quality of the structure in many different ways, and then use those as some mixture of those as a way to serve up the structure that's most appropriate for particular users. And we've been talking about images a lot, and I just want to mention that there's actually several places right now where people can deposit or have their Aura images made available. And one is Vladek's site that he talked about earlier today, which is just super great, and it's really wonderful to see that. That's going to be a way to download images from a number of different places, and with a lot of analysis that goes with them. Also, the SB Grid, which is an organization that supplies crystallographic software, many different types of crystallographic software as a big package to many structural biology groups, and which also has access to cloud computing. They also have a system for depositing raw diffraction data for their users. So those users can also do that. So in summary, I think everything I said is perfectly obvious, and I'm really glad that today it's obvious, even if it wasn't a few years ago. And I think there's a really great future for continually updating what's in the PDB, making the structures more and more accurate, making them more and more comprehensive, and serving up the right structures to the right users. Thanks.
Thank you very much, Tom. The mic's gone on the blink here. This one.
And also, I have two comments I saw from. One is the idea of versioning of the entries in the PDB thank you. The idea of versioning of entries in the PDB is a good idea, but it's almost a paradigm shift for the PDB, because I guess up to now, the basic unit of the PDB has been the model, right? It's been the coordinates, and for the longest time, even structure factors were not required, were not recorded. And so what you're proposing is basically making the structure factor the basic unit of the PDB, which I think is a good idea, and will be very helpful.
So can I respond to that one first? So the PDB has been giving very positive indications that they really like this approach and would like to do something along these lines. So I'm anticipating this will happen, and soon.
Okay. So the second comment is something going back to the whole metadata idea. You said that, and everyone knows that, I guess, with more modern software, more modern approaches, you get better models, better structures from the same data. And that, I guess, flies in the face of the idea of the user during the time of the experiment making a decision of which metadata to record and which compression algorithm to use for his project, because in the end, the whole long-term storage is not about this person's project, but again, it's more about the data themselves, right? So how do you make this decision of what you want to record, how you want to compress for it to be useful down the road?
Yeah, I think that's a really important question. I don't know the answer to that, of course. So the user at the time of collecting the data or at the time of deposition doesn't know what 10 years from now, 20, 50 years from now, somebody will want to do with that data. So the more accurately, the more comprehensively we can save the information that we do have about the data, the better off we'll be. As I sort of maybe facetiously said earlier, today the default is highly lossy compression, which is basically interpretation of the data and saving merged structure factors. That's the default, okay? And that's not so bad. We're doing pretty well, and that's way better than not having structure factors at all. So every incremental thing that we add beyond that is just a plus. And the more of those we have, the better off we'll be. And yeah, I can see somebody a long time from now having some idea about how to interpret all these things, and they'll go through the whole protein data banks of 10 million structures, and they'll redo them all, analyzing something that we never thought about at all. And I think that would just be fantastic.
Tom, I think that you made extremely good point that we really do not know what we should do, because we are working in fast prototyping mode. How I know that it's 192 frame formats, at least 192, because I encounter 192, but somewhere there may be more. And the same we have with structures and metadata. We do not, as long as we do not have even basic metadata set for all PDB, we really do not know what we can do with that. Yes, or
Yes.
with images.
Agreed.
So this is a repeat of a comment I made earlier, but outside of this session. Instead of worrying about the fact that there are so many different frame formats, why not make it part of the archiving process that everything gets transformed into the same frame format? Then it's just one place that has the same frame formats, and you don't need to worry about it, right? Then the PDB has only CBF. I don't know, it doesn't have to be CBF, but the PDB only stores one type of frame, and then everyone can reprocess it using whichever software they want. So you essentially turn the frame format problem over to the archivers.
Yeah,
So
actually, I am personally totally in favor of this idea. And my interpretation of that is that the software developers like Vladik and company have a mechanism for taking 192 different whatevers and turning them into something internal that is one version. So yeah, I'm looking for Vladik to answer this. And then presumably that thing could be written out.
Exactly. So
And presumably that thing could be standardized because it's only 5 people doing it instead of 300 people doing it. And I think if that would be possible, it would be really fantastic. Yes.
So I think that future-proofs the problem at least a little bit. And I had one second comment, which is really minor, and that's if you're starting to talk about taking multiple versions of a file and then giving data to choose which one is the best one, do you then need to introduce a new phraseology? I mean, you've got data about data about data. Maybe that's not metadata, it's hyperdata.
Yeah, perhaps so. And, you know, better is the wrong word to be using for sure. Yes,
yes,
logic.
obviously, internally we have our own frame format.
Yes.
Yes, otherwise we would went crazy long time ago. I mean, I am crazy. I realize that, but that's crazy.
Yes.
And we have a procedure to write in that format. Unfortunately, it's not so easy. Yes, to write, because it's relatively easy to change the goniostat outside. If you are learning after some time that this goniostat is not accurate, you would have to rewrite all this data. Yes, you would have to rewrite all this
I
data.
see. So your interpretation, your internal data is actually interpreted data that
Yes.
depends upon parameters which may or
On
may
all
not be. They're
parameters
not-
which
so
are
it's-
in dev side.
So it's a little
Yes.
far from the original, which is a bit. You don't think it's risky? It sounds risky to me. Yes. Yeah.
Yeah, and you see that it's even more complicated because, look, we are getting data from, let's say, beamline A. Yes, and we are doing, and they send one data set. They are saying it's extremely urgent because users are coming tomorrow. We have to have something. We are doing that. We are giving them. 3 months later, we are learning that it's really not the one frame format. There are 2 frame formats. Yes, and already some people use this other frame format. Yes, I mean, you see that as an example of the company which does not exist as a valid company is ADSC detector, extremely good detector, which had software binning and hardware binning. And companies, they do not know which one is better. So they are saying, okay, we will leave that to users. But they are not saying anything about that. Yes, we are getting data, and error density, so-called error density parameter, is different for these two. Is different by the factor of 5. And overnight, you are learning that some people who use, let's say, software binning, when you got hardware binning, they have worse resolution than they obtained before. So these are the problems which we have. I mean, we, the people who develop software, processing software in real life.
So can I propose an alternative version? So still, a user who takes your software and produces intensities out of it, you and the user have gone through a process there with the little handshake that says you understand their inputs and are able to interpret those inputs in terms of parameters that you need, namely all the angles, all the geometry, whatever. Could you not write out that information, which I think you are doing, that information which is sufficient to reproduce the experiment, the analysis with your software, and also with another, you're writing it out so that XDS or somebody else can also do that. That's halfway there, and it seems like that depositing that would be very, very beneficial.
Mike Wall.
Right, Mike Wall, Los Alamos. The question I have has more to do with my perspective viewing the protein structure as an ensemble rather than a single structure. So in a kind of Bayesian way, you can define a likelihood for different models depending on the data, and some models more likely than others. So the approach that you described seems fine of reporting one structure to a user, assuming that this likelihood function is very sharp. But if it is broader, then it might be good to actually force a user to pay attention to multiple models and instead of presenting one, especially if what they're going to do with it will yield a different answer depending on like which one they choose. So what you described is like a huge advance over the way things are now. What I'm describing is something that I guess would go somehow beyond that. So how far are we from doing this next step?
So Mike, I totally agree. I didn't talk about that today, but actually that is an issue that I feel is very, very important. That basically we shouldn't be representing these structures as a single structure as one in the beginning. That's wrong. It's not what's in the crystal. The crystal has millions of structures in it, and some representation of what those structures are is where we have to eventually go. And so I totally agree with your point.
So I'd like to also consider the end point here. So we have the better process, the continual improvement, so we get to this better use of the data through the communal efforts. So now to pose the well-rehearsed question on behalf of Durward Cruikshank, who passed away a few years ago, whose first paper on understanding the precision of coordinates in crystal structures was 1949. So in looking at what we do, he was very concerned, and it's perhaps more the matter of the graphics representation software that we all use, of having a uniform view of the precision of non-bonded distances, 2 decimal places, and he said that just cannot be true. Just look at the B factors. If 2 atoms are, potentially interacting and they're 80 angstrom square, then you're looking at integer precision of their distances apart, let alone 2 decimal places. So we have our 500 million downloads per year of the fruits of our research, and these are not specialists in our techniques, and they go away with a false precision. So he thinks, and I agree with him, forced to agree with him, he had me on the ropes, this is a big issue for our field, and maybe it's solvable by education, and all that the PDB is doing, like we heard, we saw a precision on a wavelength to 7 decimal places this morning, and it's just the over-enthusiastic computer scientists providing all of these columns for our experimental parameters and our results. But there is an issue here. I think he's right. Yes, it's an ensemble of structures because we have millions and millions in our sample, but that variation, let's perhaps avoid the word coordinate error, but coordinate variation tells us that we have to provide to non-expert users a much better feel for what the atom placement precision is.
Yes. So I, once again, totally agree with this. So actually, let me make a little point here. We need to differentiate between 2 types of imprecision or uncertainty. One is, in the actual crystal, there's millions and millions of different protein molecules, or whatever they are, and everyone is a little bit different, right? And so that's describing what's actually in the crystal. And also, these are not necessarily just Gaussian distributions that are represented simply by nice little B factors. They may be static disorder, may be many different things that can be going on. So what's in the crystal is fairly complicated and is not well represented by a single model. It would be better represented by a single model plus some numbers that say what the variation is. That would be a better step, which we aren't even doing. So that would be the first order improvement, would be what's the variability in the crystal for those numbers, right? And then second order would be something about what are the different conformational ensembles that describe most of the variation, or something like that, right? So that's where Mike's going too. So that's one thing, but separate issue is we're using our crystallographic tools to try to describe the structure, and we come up with models, and there's some, if we did the same experiment twice, we'd come up with different models. And how much do those vary? And so surely that second variation is a lower bound on our uncertainty of what is in the crystal, itself, right? So the crystal varies, and we don't even know what's in the crystal. So we need to describe both of those things, and I think ultimately we're going to describe both of those by some way of talking about ensembles of structures. And it may be molecular dynamics simulations that kind of give us a handle on how to describe that. It may be we have a limited number of ensembles that describe most of the variability, and that's what we're going to report. But absolutely, the end user has to understand what they can know from what we're telling them and what they can't know. And right today, you give them a single structure, and they look at the distance between two atoms, and they think these things must be hydrogen bonded because they're, you know, the right distance apart. But maybe it's that way only 1,000th of the time, and most of the time there's some other completely different configuration, right? And we're not telling them that today. We're not even telling them. It's ridiculous. So I totally agree.
I hope the Commission on Biological Macromolecules will take this up under your leadership.
Great.
So again, it's just another comment. You said if you take two crystals and do the diffraction experiment, you get two different models. If you take the same crystal and the same data and process it in two different ways, you get two different models.
Yes.
So it's even worse than two different crystals.
Yeah, yes, absolutely true. Absolutely true. Actually, the good thing is, so we studied this a little bit a few years ago with just macromolecular structures and just reinterpreting the exact same crystal data, just running it through our software a bunch of times with different random seeds. And the good thing is, like in a macromolecule, the core of the molecule, they just superimpose like extremely closely. You just can't do you can't interpret these structures any other way other than to basically put these atoms in pretty much the same places. But the stuff on the surface varies a huge, huge amount, yes.
Okay. Thank you very, very much indeed, Tom, and I'm sure everybody wants to show the usual appreciation. Thank you very, very much. So Brian will reconfirm the logistics, which is 7 o'clock minibus outside the front, and enjoy, I don't know, an hour and a half in the pool or whatever takes your fancy. Thank you.